Hello students, in this video we are going to discuss about the mutual inductance of two long solenoids. Actually, we are going to find an expression for mutual inductance if the two coils that we are using are long solenoids, and we will also discuss the factors on which mutual inductance depends as well as the coefficient of coupling. So these three things we are going to discuss in this video. First we will start with the expression for the mutual inductance of two long coaxial solenoids. So we are taking two solenoids S1 and S2. These are two long solenoids of length L, as well as these solenoids are axial. So what we have is two long coaxial solenoids S1 and S2. Now this in this particular case we are taking that S2 is wound over S1, S2 wound over S1. That means S1 is the inner solenoid and S2 is the outer one. So this we are considering that S2 is wound over S1, L be the length of each solenoid. For both this length is L, and R1 and R2 are the radii of two solenoids. Length is common for both, and R1 and R2 are their radius respectively. So if we have to find the area, it will be pi r1 square in case of S1, and area of cross section for the outer one, that is S2, is pi r2 square. And we are also considering that the number of turns in two solenoids are N1 and N2. So N1 and N2 are the number of turns in these two solenoids. This also we are considering. So in the diagram we can see the two solenoids S1 and S2, where S2 is wound over S1, current I1 is flowing from S1 and I2 from S2, length of each solenoid is L, and the radii are R1 and R2 respectively. Now first we are going to pass a current who is changing. We are passing a varying current I2 through S2. So what we are doing first, we are passing a varying current I2 through solenoid S2. Now because of this current I2 that we are passing, a magnetic field is set up inside S2. Now the magnetic field inside S2, because of this current that we are passing, is B2, and we know that the magnetic field inside set up inside a solenoid is mu naught Ni. So it will be B2 is equal to mu naught into I2, where N2 is number of turns per unit length, that is N2 upon L. So N2 is number of turns per unit length. Capital N2 was total number of turns in the length L, and it is number of turns per unit L. So this is the magnetic field that will set up in the solenoid S2. Now because of this magnetic field, a magnetic flux linked with the solenoid S1. Okay, so this magnetic field is the reason for the magnetic flux that is linked with solenoid S1 and is keep on changing when the current I2 vary. क्योंकि I2 varying current है, so this field will vary, and because of that the magnetic flux linked with S1 because of this magnetic field will also vary. So now we are seeing the magnetic flux. Total magnetic flux linked with inner solenoid, that means linked with S1. Because of this magnetic field B2, it will be first का magnetic flux है, so it will be phi 1, but it is because of the magnetic field B2, so it is B2A and N1 because there are N1 number of turns in total. N1 number of turns in total, that's why it is B2A N1, and A is the area of S1, area of cross section of S1, so it will be pi R1 square. So we get mu naught N2 I2 A N1. This is the value of phi 1 for the solenoid S1. Now we can find mutual inductance of first solenoid with respect to 2. So mutual inductance of coil 1, or we can say it as of S1 with respect to coil 2, that means of with respect to S2. So it will be M12. So M12 represent inductance, mutual inductance of 1 with respect to 2. That means when you were changing current in 2, there is some magnetic flux linked with the coil 1. So M12 is equal to phi 1, flux of 1 and current of second. So it is phi 1 is equal to mu naught N I2. Now this is N2. B2 में this is N2. N2 I2 A N1 capital N1 upon I2. I2 and I2 will cancel out and it will become M12 equals mu naught N2 A, and capital N1 को हम लिख सकते हैं N1 into L. So it will be mu naught N1 N2 A L, or in terms of capital N it will be mu naught N2 को अगर हमने लिखा होता then it will be N2 A N1 upon L is equal to mu naught N1 N2 A upon L. Here capital A was the area of cross section of inner solenoid and value for A is pi R1 square. Okay, so A is the area of inner solenoid. Now we'll talk about the mutual inductance of second coil with respect to the one, that is M21. So for that we have to pass a current, a varying current I1 through S1. Field B1 will be set up in the coil 2 because of coil 1, right? So field setup होगा B1 and उसकी वजह से magnetic flux link होगा second coil में. So now we are going to pass K second में we are going to pass a varying current I1 through S1. Because of that S1 में magnetic field आएगा B1 which has value mu naught N1 I1. Now because of this magnetic field there will be a magnetic flux linked with the second coil. Now this is the field in 1 and because of that there is a magnetic flux linked with the second coil. So total magnetic flux linked with S2 will be phi 2 is equal to B1 A N2. Now the catch is what will be the value of A here. वहाँ पर S1 के केस में there were the area of first coil only, that is pi R1 square. Now in case of the second coil this A should be pi R2 square, but it is not so. Okay, this time also the value of A is pi R1 square. This remains common. Now why we are taking this, we have two coils in which the inner one जो अंदर coil है that is S1, right? S1 is the inner coil, means S2 or S1 में when we are talking about mutual interaction the area that is common is the area of S1. Okay, suppose we have a big cylinder and inner to that we have a smaller one. The smaller one has the radius r1 and the bigger one has the radius r2, and r1 is lesser than r2. Okay, so now if I want to find the area in which is common to both, or in which the flux lines because of the magnetic field in first, so we get the area this much, means the cross section area is of the radius r1. इनिशियल केस में क्या था, हमने फील्ड प्रोड्यूस किया था इन R2 means the bigger one, and because of that flux is linked with the whole region, and the region that we have to consider is of r1 radius, so we consider A is equal to pi r1 square. In this case we produce field in the region of radius r1 only, so there is magnetic flux in the region r1 only, although we have second coil of radius r2 which covered this much larger area, but the magnetic flux is passing through the area of radius r1 only. There is no flux in the region that is more than r2. So in this case also the value of capital A will be pi r1 square. This we have to note or remember while doing this derivation. Okay, so now we have phi 2. When we have phi 2, we can find mutual inductance of second coil, that is S2, mutual inductance of second coil with respect to first coil, means we are going to find M21. Now this is because of phi 2 upon I1. Current was in first coil, and because of that flux linked with the second coil is changing, so phi 2 upon I1. The value of phi 2 is B1A N2 upon I1, and the value for B1 is mu naught N1 I1. So we are going to substitute this mu naught N1 I1 capital A N2 I1. Now I1 and I1 will cancel out, and the answer that we will get is M21 is equal to mu naught N1 N2 A. This is the answer. Now we can write it in the terms of small n2. So M21 will be mu naught N1, and capital N2 ko we can write N2 into L A. So it will be mu naught N1 N2 A L, or in terms of capital N it will be mu naught. We can write N1 as capital N1 upon L, capital N2 A. So it will be mu naught capital N1 capital N2 A upon L. So these are the values for mutual inductance of second coil with respect to first coil. Now if we compare both the results, what we see is M12 is equal to M21. So let it be capital M. We assume it as capital M. अगर हम दोनों आंसर्स को कंबाइन करेंगे then we get that M12 is equal to M21, and we call it as capital M for both the coils mutually. So M is the mutual inductance of two coils, and it is the property of their combination. For a particular set of coil it will remain same, and its value will be mu naught N1 N2 AL, or mu naught capital N1 capital N2 A upon L, and the area A is always is equal to pi r1 square, that is the area for the inner coil. Capital A is the area for the inner coil. So mutual inductance of two coils is the property of their combination. This we have to note, that M means mutual induction is the property of combination of two coils. Now it doesn't matter which one of them is functioning as a primary coil or secondary coil, the value for mutual inductance will remain same. Means if we find M12, if we flow current I1 from S1 and see how much current is induced in I2, or vice versa, in both case the value for mutual inductance will remain same. It is a property of combination of these two coils, and it doesn't matter which one of them is primary and which one of them is secondary, and this property is known as reciprocity theorem. So that means any of the coil in combination can work as primary and secondary coil, and it will not affect the value of mutual inductance if the coils are same. If we change the coil, then it will be something else, but if the coils are same, only their functioning is changing. Like sometime one coil is primary while the other is secondary, and after some time they are changing their work, means primary works as secondary and secondary works as primary. In that case the value of capital M will remain same, but if we change the coil, in that case it will be different. So for a particular combination of two coils, the value of M remains constant. This is the mutual inductance of two long solenoids. Now we are going to see what are the factors on which this mutual inductance depends. So the very first factor on which the value of mutual inductance depend is the number of turns of two solenoid. If we see the formula of M, it has N1 N2, capital N1 capital N2 in numerator. That means M is directly proportional to the product of N1 and N2. So the very first factor on which it depends is number of turns. Larger the number of turns in two solenoids, larger will be their mutual inductance. This is the first factor. The second factor is the common cross sectional area, that is capital A, which is equal to pi r1 square. So that is common cross sectional area. So larger the common cross sectional area of two solenoids, larger will be their mutual inductance, because mutual inductance is directly proportional to capital A. Now the third factor is their relative separation. Now we are also considering the separation of two coils. Larger the distance between two solenoids, smaller will be the magnetic flux that is linked with the secondary coil due to the current in primary. Hence the value of M will be small. So it is a simple one. We are talking about the separation or the distance between the two coils. So if this relative separation is low, अगर relative separation low होगा, that means the two coils are have some distance between them, are थोड़ा दूर हैं वो एक दूसरे से, and because of that the magnetic flux that is linked with the secondary coil because of the current in primary coil, right? The magnetic flux linked with the secondary coil because of the current in primary coil will also be less, and if this magnetic flux is less, the value of M will also less, because it depends, M depends on, M is equal to phi S upon IP. We know this formula that magnetic flux equal होता है, म्यूचुअल इंडक्टेंस इक्वल होता है मैग्नेटिक फ्लक्स अपॉन करंट के, वेयर फ्लक्स इज ऑफ द सेकेंडरी कॉइल एंड करंट इज ऑफ प्राइमरी कॉइल. So if the two coils are separated, this value of flux is smaller, and because of that M will be small. So this is the third factor on which mutual inductance depends. Now moving to the fourth one. Fourth is the relative orientation. Relative orientation of the coils. Now in our example we consider the two solenoids as coaxial, like this. Now these two coils can be coaxial or these two coils can be perpendicular. This case was also possible. So the value of mutual inductance also depends on the orientation, because M is maximum when entire flux of primary is linked with the secondary coil. अगर फर्स्ट का entire flux, complete flux secondary coil से linked है, then in that case the M is maximum, while if it is not so, it is not at maximum, and it is minimum when the two coils are perpendicular to each other. So orientation also matters. That means M is maximum when primary coil P envelopes secondary coil, and M is minimum when P is means primary coil is perpendicular to secondary coil, and in between these two positions it will vary between the value of maximum M and minimum M. So orientation of the coils also matter when we are talking about the value of mutual inductance. Now the last but not the least is the fifth factor, that is permeability of the core material. This we have also talked about at the time of self inductance. It is same in this case. If the two coils are wound over an iron core of relative permeability mu r, then their mutual inductance increases, and it will be mu r times of its initial value. Means initially we have two coils having some value of M. I am considering its mutual inductance is capital M for any two coil. Now if I wound those two coils over an iron core with permeability mu r, then the new value will be mu r into M. That means the permeability of the core material also affect the value of M, and it simply becomes mu r times of the older value of M, right? So this is the permeability of core material, and it increase the mutual inductance by mu r times. These are the factors on which capital M depends, that is the number of turns, common cross sectional area, separation between two coils, orientation of two coils, and permeability of the core material. Next thing is the coefficient of coupling. Now the coefficient of coupling is actually the measure of manner in which the two coils are coupled or linked together. So this is the thing. Coefficient of coupling tells us how closely these two coils couple together, and if they are coupled quite close, then their mutual inductance is also high, because the value of magnetic flux linked with the two is also high, right? So coefficient of coupling gives us an idea how the two coils are coupled together. If we have two coils and these two coils have L1 and L2, their self inductance, okay, so we have two coils, L1 and L2 is their self inductance, and M is their mutual inductance. There are two coils who are linked together. These coils have L1 and L2 self inductance separately, and when they are coiled together, coupled together, their mutual inductance is capital M. Then the coefficient of coupling can be given as K. K is the coefficient of coupling, and it's given as M upon under root L1 into L2. Okay, so K is equal to M upon under root L1 into L2. This is the value for coefficient of coupling, and K always lies between 0 and 1. The value of K lies between 0 and 1. Here 0 shows that there is no coupling. 0 का means क्या है? There is no coupling, no flux is shared by the two coils. That means mutual inductance is 0. K की value 0 means no coupling, M is equal to 0, and the value of K1 means maximum coupling, and M is at its maximum value. K is equal to 1 means there is maximum coupling, M is at its maximum value, or we can say that entire flux of primary entire magnetic flux of primary is linked with secondary coil. So K0 means no coupling and K1 means maximum coupling. The value of K is M upon under root L1 upon L2. So K is maximum for the coupling and minimum for the coils. Those are not coupled. Okay, so this was the coefficient of coupling. That's it for the video. For next videos, stay tuned and keep studying. Thank you.